integrals that have infinite limits. That's how I'm going to define it. These are basically integrals that have infinite limits. So the good news is there's nothing new in this section. In other words, there's no new integration technique. The only thing is I'm going to give you an integral, something you might have done before, but I'm going to have additional limits, and one of which might include infinity. For example, the integral of 1 over x minus 1 as x goes from 2 to infinity. Okay, when you do these questions, at first completely ignore the limits. Just do it as any other integration question, and then we can worry about the limits. And when you have an infinity as one of your limits, don't be surprised if you have to use L'Hopital's rule. And thus, we studied L'Hopital's rule prior to this section to prepare you towards finding such limits. Okay, so forget about the limits of integration. What is the integral of 1 over x minus 1? The integral of 1 over x minus 1. ln x minus 1. We did all these complicated ones. We forget the easier ones, right? ln x minus 1. But now we have limits to deal with from 2 to infinity. Okay, what is ln of infinity minus 1? In other words, what is ln of infinity now? First of all, what is infinity minus 1? That would still be infinite because you have x meaning a quantity getting larger and larger, minus a constant, still a quantity getting larger and larger. So you still have infinity there. So what is ln of infinity? Think about the graph of ln function. Where does it go as x goes towards infinity? It keeps getting larger, so infinity. Minus, plug in the lower limit now. That's ln of 2 minus 1 or 1. And it could have been any constant. It wouldn't have made a difference. Infinity minus a constant number is still going to be infinity because, again, infinity basically represents a quantity getting larger and larger in these examples because we're taking a limit as x goes to infinity. So the answer is infinite. Now, what I did here is actually I took a little shortcut. I also like to show you how the book does these questions, and then you decide what you're comfortable with as you're solving these examples. Okay? Here's how the book defines an infinite limit. They say, okay, if you have integral from a to infinity of f of x dx, this is going to be the same thing as limit going from a to t of f of x dx, but as t goes towards infinity. Let me show you with a picture what we mean by this. See, this is your function f of x. Say this is the point A. And to answer the original question, to find the integral from a to infinity of f of x dx, basically you would need to find this area under this blue curve, which we call f of x function. So what the book is saying is what you can actually draw a finite line in there somewhere. Draw a finite line, call that t. Okay. So first find the area of the finite region from a to t of f of x dx. And then what do? We let t get further and further away. Let t go towards infinity. As you see, it's sort of this limit. So that's how they define an infinite integral, or an integral with infinite limits. You can do it this way. So if you did this about problem with that technique, you would have to write the following. You would have to write here, limits as t goes towards infinity, ln of x minus 1 from 2 to t. So basically, instead of plugging infinity right away, they're taking a limit as t goes to infinity, but it turns out to be the same answer. I like my method better because from the past experience, I've seen students get very confused with the notation and not getting down to the bottom of things. So I'm going to use a shortcut notation. Just be aware of the book's notation. In case you prefer that, you're certainly welcome to use it. Okay, here's another example about an improper integral. Maybe there was a point back in history where these were really improper. People said, oh, no, we can't touch these integrals. They cannot be done. But today, with the help of limits, we can handle integrals with infinity as one of its limits of integration. Okay, let's do the integral of e to the negative x. As x goes from 0 to infinity. First, forget about the limits, right? Let's first find the integral here. What is this integral? How do you integrate e to the constant times x? Say e to the 5x. How do you integrate e to the 5x? E to the 5x divided by 5, right? Here it's e to the negative x, so the integral will be, the antiderivative will be e to the negative x divided by negative 1. But I might as well just put a negative 1 up front here. And the limits are from 0 to infinity. Okay, now is our question, how do you handle the case negative e to the negative infinity? It might help to rewrite it as follows. This is negative 1 over e to the x, right? It helps to rewrite it like that and look at the limits one more time. And remember, anytime I have an infinite limit, what I really mean is take the limit as x goes to infinity. So in this case, looking at the upper limit of integration, where does this quantity approach as x approaches towards infinity? Where does 1 over e to the x approach? 0, right? So that's the upper limit of integration handled, 0 minus, now let's plug in the lower limit of integration. As x goes to 0, in this case equals to 0, 1 over e to the 0 is 1, but don't forget there's an extra negative there. So what is our final answer? Positive 1. Okay. One more example. The integral from negative infinity to 2 of 2 over x squared plus 4. Once again, the moment we see an infinite limit, we'll ignore the limits of integration at the beginning of the problem. Just worry about how you would integrate the given function. Does anybody recognize this as a special formula? Do I need partial fractions here? Do I need U substitution here? Absolutely not, right? The simple rule of arctangent applies here, right? The 2 on the top can be factored out first of all. Now you have 1 over x squared plus 4. What is the antiderivative of that? One over a. What is our a? Times tan inverse of x over a. And the limits are negative infinity to 2. These are gone. So plugging the upper limit of integration, you have tangent inverse of 2 over 2, or 1. Plugging the lower limit of integration, we'll come back to that in a minute. Plugging the lower limit of integration, I'll have tangent inverse of negative infinity over 2, but that's still negative infinity, right? An infinite quantity, if you multiply it or divide it by a positive constant, it's still going to keep its infinite identity. Okay, tangent inverse of 1. At which angle is the tangent function equal to 1? At which angle in radians? Pi over 4, as Joshua suggested, pi over 4. And this is where you need to remember that information from the last section. Tangent inverse of negative infinity. What do we know about that? Tangent inverse of negative infinity. Negative pi over 2. We just went over that. So the answer is pi over 4 plus pi over 2. 3 pi over 4.
Professor, why, how do you go from infinity?
All right, so here is one more example of improper integrals. Let's find the integral of x times e to the negative x dx, and the limits are from 0 to infinity. Okay. Once again, forget about the limits. How would you normally integrate x times e to the negative x? Can we use u substitution? The answer is no. Can we use integration by parts? And there the answer is yes. So we're going to begin by applying integration by parts. So let u be equal to x and dv be equal to e to the negative x, so that du is dx and v is negative 1 times e to the negative x. Based on the integration by parts formula, I need u times v minus integral of v du. Call that I. Moving down here, I equals negative x times e to the negative x. And I have a plus the integral of e to the negative x dx. And once again, that integral will be e to the negative x divided by negative 1. In other words, minus e to the negative x. And now we can worry about the limits going from 0 to infinity. I'm going to rewrite everything that has e to the negative x in it as 1 over e to the x. So the first term is negative x divided by e to the negative x minus 1 over e to the x, everything going from 0 to infinity. Okay, if we look at the first term here as x goes towards infinity, notice we're going to have, as a matter of fact, since I put e to the negative x in the denominator, I should have it as e to the plus x in the denominator. So the first term is negative x over e to the x, and the second term is minus 1 over e to the x. And now I'm trying to find out what happens as x goes towards infinity. Again, the first fraction here is of the form infinity over infinity, and therefore we can use L'Hopital's rule that we have just learned. If you differentiate the top, you get negative 1. If you differentiate the bottom, you get e to the x. Now try to find out what happens to this quantity as x goes towards infinity. And this quantity approaches towards 0, right? Therefore, the original quantity approaches towards 0 as x goes towards infinity. And we're not done, because infinity should also be substituted for the second fraction. In other words, take the limit as x goes to infinity of 1 over e to the x. That also goes to 0. Minus, now substitute 0 into the first fraction. 0 over a constant is 0, minus, now substitute 0 into the second fraction. There we have negative 1 over e to the 0, or negative 1. Distributing our negative signs, we end up with positive 1. So that is the answer to the original integral question from 0 to infinity. The answer is 1. Okay, one more example of improper integrals. Let's find the integral of 2 over x squared minus 1 from negative infinity to negative 2. Okay, let's think for a moment. How could we go about integrating this function? Again, the limits look confusing. There's an infinity in there. It looks like it might be complicated. you know, half the credit for the question, or maybe even more than half, is doing the antiderivative process. So ignore the limits for now and try to integrate 2 over x squared minus 1. Okay, we know we cannot use u sub. There is no x on the top. We cannot use the arctangent formula. There is no plus in the middle there on the bottom. Let's try to factor the bottom as x minus 1 times x plus 1. So does any other techniques come to mind? Yes, if you said integration using partial fraction decomposition, you were right, because this integral can be written as a over x minus 1 plus b over x plus 1. Getting common denominators. And setting the numerators from the left-hand side and the right-hand side equal, we get this equality. Now to find a and b, first let x be equal to 1, then let x be equal to negative 1. If x is 1, we get 2 equals 2a, so a equals 1. If x is negative 1, 2 equals negative 2b, so b is negative 1. And rewriting the given equation, since a is 1, we have to integrate 1 over x minus 1 plus, in this case, minus 1 over x plus 1 dx. By the way, if you're ever in doubt as to whether your partial fractions are correct, you could go back and try to add them up and try to get a single fraction with a unique denominator, and make sure that that fraction really is the fraction that you started with. Okay, now integrating each one of these is going to be very straightforward, right? First one is ln x minus 1, the other one is ln x plus 1 in absolute values. And I can rewrite this as a single logarithm of x minus 1 over x plus 1. And now I'm going to worry about the limits from negative infinity to negative 2. Okay? Starting with the upper limit of negative 2, I will have ln of negative 2 minus 1, or negative 3. And then on the bottom, negative 2 plus 1, or negative 1. Minus, now think about what happens as x goes towards negative infinity. At this point, you will have negative infinity over negative infinity, very much like infinity over infinity. So you can actually apply L'Hopital's rule. And alternatively, you might remember from Calculus 1 that if you have x minus 1 over x plus 1, if the degree of the top is equal to the degree of the bottom, then the limit is going to be the ratio of the leading coefficients. In this case, that will be 1. So then we have ln of 1 is the end result as we calculate this expression as x goes towards negative infinity. And we know that is 0 anyway. So our final answer turns out to be ln of 3.